Before we dive into multivariable calculus, let's take a second to think philosophically. Here's a quote from Galileo. So according to Galileo, mathematics is the language of nature, is the language of the universe. Well, if that's the case, then I contend that calculus is the poetry of nature. If calculus is the poetry of nature, we must somehow be able to describe natural things, or nature, with mathematics and with calculus. And the way we do that is by mapping numbers to objects. Now, in applied math, we map numbers to real things, and in pure math, we map numbers to mathematical objects in some way or another. But we need to be able to discuss things in terms of numbers, whether those be concrete numbers or whether they're abstract numbers. We need that mapping. Lord Kelvin said it like this. So we need this way of describing things, describing objects, whether they be abstract mathematical objects or real-world objects with numbers. There's several ways we can do that. Let's just start with the most simple. The most simple way is looking at collections of things, and this is sort of where our idea of number started. We have 5 apples here, so this clearly, we can use the number 5 here to represent this group of apples. So that's one way we can use numbers to describe things. But very quickly, that becomes limiting. If you wanted to say, describe a table, let's draw a quick table here. If I wanted to say describe this table with a number, what number would I give it? Well, we could describe it with its width. Maybe its width is 6 feet. Maybe we could say its depth is the number we want to use to describe it. Maybe its depth is 3 feet. What about its height? Maybe its height is 36 inches. We could use any of those 3 numbers to describe the table, but one of them on its own is not sufficient to describe this table. And that's a difficulty we run into in math, is when one number is not enough. All right? You already have a lot of experience with this. Maybe you didn't know it. Whenever we use the Cartesian plane, we need more than one number to describe a point. If I wanted to describe this point on the Cartesian plane, how would I do that? One coordinate is not enough. I need to know that we went 1, 2, 3, 4, 5, 6 over, and I also need to know that we went 1, 2, 3, 4 up. So I would describe this particular object or place or location with the numbers 6, 4. Okay, so here we have 2 numbers used to describe a thing, a point. What if the object we want to describe, or the point, is in 3 dimensions? So this ball right here floating in 3-dimensional space. How would we go about describing that? A point floating in space can be described using 3 coordinates, or 3 dimensions. Here we have 3 axes, the x-axis, the y-axis, and the z-axis, and we can use these to help describe our point. So if we're going to try and describe this point in reference to the origin right here, then we would want to know how far along the x-axis we have to go. We'd want to know how far along the y-axis we have to go, and how far along the z-axis we have to go. It's standard for this to be known as x, this to be known as y, and this to be known as z. So to determine the coordinates of a point, we just measure the distance from each of the 3 axes. For this point, we can see that the x-coordinate is 2, the y-coordinate is 4, and the z-coordinate is 3. But it doesn't have to stop there. What if I wanted to describe, say, the stock market? We can use indicators of the stock market, like the Dow Jones Industrial Average. Now, the Dow Jones Industrial Average gives us one number, 14,000, something like that, which describes the entire stock market. But is that a perfect indicator? Perhaps not. Perhaps we want a little bit more information. Well, we could construct a list of all of the stocks in order, and that list would be a descriptor of the stock market. Again, multiple numbers. So you can think of these as coordinates: the x-coordinate, the y-coordinate, the z-coordinate, the w-coordinate, the whatever coordinate. In general, because we don't really care in mathematics how many coordinates we need to describe something. All we care is what those coordinates are. Once we get into multiple dimensions, very quickly x and y lose their value. So we just call it x1, x2, x3, x4, dot, 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 x sub n, etc. So we can have a list of numbers to describe something that is any length we like. Let's give these lists name. So I'm going to call my first list V, and it's just x1, comma x2, dot, dot, dot. I don't even care how long it is. So the question is, when we deal with numbers, we know how to deal with them. For example, we know that 1 plus 3 is 4. We know that 6 times 2 is 12. We know that 24 divided by 8 is 3. Okay? We know how to work with these, how to work with numbers very well. But what do we do when we have these lists of numbers? How do we combine them? So let's say we wanted to talk about these four companies here. We want to talk about these four companies. We have Facebook trading at 19, Apple trading at 677, Microsoft trading at 31, and Google trading at 698. Now these are all somewhat realistic numbers, but they're not exact. So don't quote me on this. We might represent that with a list of numbers, which we could call that list of numbers, let's say S for stock, or maybe P for prices, but we could just call it S. And we could say it's 19, 677, 31, and 698. Now the first thing you're going to notice here is that the order matters very much. Okay? Facebook is listed first, so I put Facebook in our list first. Google is listed last, so I put Google's price last. If I had switched the order of these around, it would have drastically changed the meaning of this object S. Now, what if I had at the same time another bit of information? We knew that on a particular day, this is how the stocks changed that day. Facebook went up by $1 or 1.2 points. Microsoft went up by 0.9 points, and you get the idea. So we could represent this by another one. Perhaps we want to call it we could call it the change in S. That would be a logical name, although we could really name it anything we like. And we would give that 1.2, negative 13.7, 0.9, and 3.6. Now, if I wanted to add these two numbers, you would probably wonder, can we do that? Can we take a list S and can we take another list, delta S, and can we add them? What does that give us? Well, the logical thing, what we would probably mean by that, would be to take the coordinate for Facebook and add the corresponding coordinate for Facebook in this list, and the same thing for Apple and Microsoft, right? And for Google and its change. So we could represent that as 19 plus 1.2 and 677 minus 13.7 and 31 plus 0.9 and 698 plus 3.6. And we would simplify that and we would get the result of adding these two lists. So that seems like a natural way to do that. But what if on a different day we had this information? Instead of learning how much the stock price changed, we might learn how much the stock price changed in a percent. Right, so in this case, we wouldn't want to necessarily add 19 or take away 2% from 19. We would, but first we'd have to figure out what 2% of 19 is, and by doing that, to multiply. So then we come into the question, we have our list S, 19, 677, 31, and 698, and then we have our change in S, minus 0.02, plus 0.0001, 0.063. I'm converting the percents to decimals, and then minus 0.038. Okay. So we have all of these, this information. How do we combine these? Can we just multiply? Can we take this list and can we multiply it in some meaningful way with that? So one way would be possibly just to say, okay, well, what I mean by multiplying is to multiply this coordinate by this coordinate, this coordinate by this coordinate, this coordinate by this coordinate, and this coordinate by this coordinate. But it turns out that there are some other situations where it might be meaningful to think of multiplication in a different way. So we have to be a little bit careful when we start to work with these numbers, right? And that's what Chapter 1 of your textbook is, or Chapter 1 and 2 of your textbook are about. They're about how to work meaningfully with these lists of numbers. A list of numbers, which we're going to call a vector, is just like a single number. From a mathematician's perspective, we can deal with vectors in the same way we deal with numbers. We can do operations on them, we can create functions of them, and because we can do that, we can do calculus on them. One other point that I want to emphasize that the textbook does not emphasize quite as much as I would like is the difference between a vector and a coordinate point. Okay, so when I think of a list of numbers, right, when I take my list of numbers, let's say I have I'm going to call my list. A is my list of numbers, and let's say A is 2, 5. Well, in order to find that, I would go over 2, and then up 5, and I would find my point. So in this sense, the list A represents a point in space. Now, in this particular case, the space is the Cartesian plane. In our previous example with the stocks, this represents a point in space also. The space, in this case, is the prices of these 4 stocks. So a list of numbers can represent a point in space, but it can also represent a vector, okay? And when we talk about a vector, really what we mean is a directed line segment, and that is the terminology your textbook uses. A vector 2, 5 means that I go over 2 and I go up 5. So the x-coordinate changes by 2 and the y-coordinate changes by 5. Now, it really does not matter where I put this in space. No matter where it is, it goes over 2 and up 5. So there's a slight difference between a point in space, which represents a specific location, and a vector, which represents a change in location. So we've already seen an example of that with our stock example, that this would represent a vector, or a change in position. The important thing to remember is that vectors are not located anywhere. They can be located wherever you like. Really what we say when we talk about a vector is we're talking about the family of vectors. All of these directed line segments represent the same vector, and that vector is 2, 5, over 2, up 5. It's convenient to write or to draw, in many cases, to draw our vectors starting from the origin and finishing at some point, where the point corresponds to the point, which is the location in space. But it's good to keep in mind that a vector, in the true sense, is not the line from the origin to that point. We just choose to represent the vector by that particular line segment. So, hopefully that gives you a little better understanding of vectors as objects of math operations, and also gives you a distinction of vectors versus points. Moving forward, you're going to learn to do arithmetic. Well, it's really called algebra of vectors, but it's really arithmetic. You're learning the rules of arithmetic, just like you learn the rules of arithmetic for numbers. You need to learn those rules of arithmetic for vectors. And then once we're comfortable with that, we will go into using functions whose arguments and outputs are vectors. See you next time.